Have you ever wondered where the formula for a geometric series comes from? Have you ever wondered why a1 plus a2 plus a3 plus plus a to the n, assuming this is a geometric series, equals a1 times r to the power of n minus 1 all over r minus 1? Have you ever wondered why that's the case? I mean, I'm sure you've probably seen this in your math class. This is probably just a well-memorized formula, but I mean, have you ever derived it? I mean, it's a very interesting problem, and it's quite enlightening to figure out how it was actually originally derived. So I've taken the liberty of just creating a video to anyone who's interested in actually finding out how this was actually derived, what you actually did to get this formula. It seems kind of like magic, but you'll find out that it's just a case of just simple logic, really. So let's begin. How about we ask ourselves from the very beginning, what is a1 plus a2 plus a3 plus plus a to the n? Assuming this series is a geometric progression. How would you do it? Well, first of all, you'll have to start off by recalling everything you know about a geometric series. Well, with a geometric series, like say this one, where it's I don't know, that's 4 plus 8 plus 16 plus 32. This is an example of a geometric series. Notice how each individual term after another term is being multiplied by 2. So 4 times 2 is 8. 8 times 2 is 16, and 16 times 2 is 32. This is how we define a geometric series. Not formally, it's basically multiplying each term by 2 as you go along. But there's a mathematical way you can write that. You can just say that the term to the right of another term divided by that previous term is equal to r, and r is constant. In other words, I could have said, in this case, that a divided by 4 is equal to 2. And we call this 2 our common ratio, r. In any case, it's just in this particular case that it's equal to 2. So let's go back to this. In this case, where we've got a very generic geometric series, we can say that our common ratio r is just a2 divided by a1, where r, by definition, has to be constant. Right? Well, that's not all we know. We also know that our common ratio remains the same throughout every number of terms. So we can basically say that also a3 divided by a2 is equal to r. Right? I mean, basically, you're timesing a1 times r is equal to a2. a2 times r is equal to a3. I've just rearranged the way it's written, but this is the definition of a geometric series. So let's use the knowledge we've got to try and find out what the sum of all this is. Well, first of all, we don't know what our answer is, so it's very typical in mathematics to let an unknown equal a variable. So how about we just let our variable equal q? We'll let q equal a1 plus a2 plus a3 plus, and it goes on and on and on until you get to some final number an. Right? We don't know what q is. I mean, it seems like this won't be helpful at all. I mean, we've just let something unknown equal to another unknown. It seems completely useless. And at the moment it is, but you'll see that it actually has a very useful property later on. Well, let's try and rearrange the right-hand side of this equation, given our information that we've gotten before. Okay, so let's begin by finding out if we can rewrite a2 as anything. Well, we already know, according to this thing, that a2 can be rewritten. We know that a2 can be rewritten as r times a1, right? If you multiply both sides by a1 in this original equation, you get a2 is equal to ra1. Well, that's easy. That means you can simply sub that one into there. Now let's figure out what a3 is equal to. Well, if we're interested in rearranging what we've got up here, we can simply go a3 is equal to r times a2. Not too special, we just multiply both sides by a2. But that's not all we can say. We can also say that a3 is equal to r times r a1, right? Because we just figured out what a2 is before. So once you sub in, you can simply go a3 is equal to r squared times a1. And you can keep doing this. So let me just do an arrow here if you don't mind. It's a3 is going to be r squared a1, right? And let me just hammer this point home. How about if we want to find a4? What would a4 be equal to? Well, we know that a4 is equal divided by a3 is equal to r by our definition of a geometric series. Therefore, a4 is equal to r times a3, which is equal to r times ra2, which is equal to r times ra1, right? It's almost a tongue twister, isn't it? And if you just multiply the r's out, we know that using index laws, we can simply write that as r to the power of 3 times a1. There seems to be a pattern occurring, and it's very important to recognize what this pattern actually is. So this is going a little bit messy, so let me just rewrite what I've written below. Q is equal to, and I won't rewrite this, but it's equal to a1, our first term, plus a2, which can be written as ra1. I'll draw an arrow to show that this is the same thing as a2, plus r squared a1. That's the same thing as a3, plus r cubed a1. That's the same thing as a4. And it goes and a4. And it goes all the way until you reach your a to the n. Now let's have a think. What would a to the n look like if you wanted to rewrite in terms of a1? Well, you can see, just by noticing the pattern here, you can go that we know that there's going to be an a1 here, but what that a1 will be times by r to some power. What will that power be? Well, just by recognizing the pattern here, if you have a 4 there, then you're going to have r cubed. If you have a 3 here, then you're going to have r squared. If you have a 2 here, then you're going to have r to the power of 1. So just by recognizing the pattern, even though you could prove this formally, you can go, okay, well, that's just simply going to be r to the power of n minus 1. This is equal to a to the power of n, your last term. Right? That's an interesting way of rewriting our geometric series. Remember, r is constant in this case. Well, that's great. I mean, I still, it seems like I haven't gotten any closer to solving the problem, but I have. What if we consider this just one equation? Right? We know if we multiplied both sides by r, we get something very, 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 I guess, well, useful. If we multiply both sides by r, we can get the left-hand side as rq, and we get the right-hand side as r times a1 plus r squared times a1 plus r cubed times a1 plus r4 times a1. And it keeps on going all the way until you get r to the power of n a1, right? Remember, if you've got r to the n minus 1 and you times it by r, by index laws, you just sum up the powers. So let me just write an aside right here. If you have r to the power of n minus 1 times by r, that's the same thing as r to the n minus 1 times r to the power of 1, which is equal to r to the power of n minus 1 plus 1. The minus 1 and the plus 1 cancels out, and you're left with r to the power of n. That's just a small aside right there. So this is what you get if you multiply this term by r. Remember, we've times the left-hand side and the right-hand side by r in this case. And we'll call this equation 2. Right? And the reason why I've separated these two equations, even though they were derived from each other, is because we're going to use simultaneous equations to try and find the answer, to try and find q. So how about if we just get, what's a good one? How about we get equation 1 and subtract it from equation 2? Well, on the left-hand side, we'll get q minus rq. And on the right-hand side, if you get equation 1 minus equation 2, you'll get a1 plus ra1, ra1 plus r squared a1 plus r cubed a1 plus plus r to the power of n minus 1 a1. And then remember, we're subtracting this from the right-hand side of equation 2 now, just using simultaneous equations. And you'll get, I'll just put a brackets around here, ra1 plus r squared a1 plus r cubed a1 plus, I'll write it out again, r4 a1 plus dot 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 dot, implying that there are many terms in between, r to the power of, actually I'll write out one extra term, r to the power of n minus 1 a1 plus r to the n a1. Right, the right-hand side of this is the exact same as this. I've just rewritten one extra term, which was previously included in the dot 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 dot. You'll see why in a second. So let's say we wanted to simplify the left-hand side. Well, it's pretty much entirely simplified, but we can factor out a q. We can go, okay, well that's just simply q times 1 minus r. Okay, can't do much more with that. Let's try and simplify the right-hand side. Well, if we just look at how many terms cancel off, we can simply just erase them. Look at this. This is going to be RA1. This is RA1. But don't forget there's a minus here. And remember, due to factorization, a minus influences every term inside the bracket. So this is going to be minus RA1. This is going to be minus R squared A1. This is going to be minus R cubed A1. I think you get the idea. So what happens is you get these terms canceling off with these ones, right? So this is RA1, and that cancels off with this, RA1. R squared A1 minus R squared A1 is 0. Minus R cubed A1 minus R cubed A1 is 0. And it keeps on going. And all these terms keep on cancelling off. You'll find out that the dot 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 all the way to R1, R to the power of n minus 1 A1 cancels off with all of these terms over here. And it will keep on going. There'll be mass cancellation. Right? Every single term. All you'll be left with by the end after cancelling off all of these terms is A1 and this term, minus Rn A1. Let's write that down. If we cancel off all these terms, we get A1 minus Rn A1. Wow, that's quite a staggering result, isn't it? We've turned something which seems to have, well, not infinite, but a ridiculous amount of terms. We don't know how many, and we've just cancelled them all off to get two terms on the right-hand side. I've always found that quite enlightening. Well, if we wanted to then solve for q, we could simply divide both sides by 1 minus r. And we get q is equal to a1, if we factorize, a1, 1 minus rn, all divided by 1 minus r. That is our answer. And don't forget that we let q equal this. So we know that this is now equal to our original formula, which was, I think, yeah, it was a1 plus a2 plus a3 plus dot 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 plus a to the n